Good day everyone, I'm Gong Wei Ting. My group will be presenting and focusing on applying artificial intelligence search algorithm to solve a road planning problem. So route planning involves finding the most efficient route to visit multiple locations while minimizing the travel distance. As the number of locations increases, finding the best route becomes more challenging. So AI search algorithms can be used to systematically evaluate possible routes and identify the most suitable solution. The objective of this assignment is to determine the optimal road that visit all 6 group member residential locations starting from Sunway University. To achieve this, we evaluate and compare 3 search algorithms which are uniform cost search, air search, and greedy best first search. For data collection, we first identify the residential location of all group members, and next, travel distance between every location were collected using Google Maps and organized into a distance matrix. These metrics provide the travel distance between each pair of locations and serve as the foundation for constructing the state space and evaluating the search algorithms. Using this data, we were able to model the road planning problems and analyze the performance of the 3 search algorithms in finding the most efficient route.
To simplify the analysis, several assumptions are made. All roads are assumed to be accessible, travel distances and time remain constant, and each residence only needs to be visited once. The journey starts from Sunway University and does not require a return trip. Dynamic factors such as traffic congestion, weather conditions, road closures, and vehicle breakdowns are excluded, allowing the problem to be treated as a deterministic and static environment. The problem is represented as a weighted graph consisting of 7 nodes, where each node represents a location and each edge represents a route with an associated distance cost. The initial state is Sunway University with no residences visited, while the goal state is achieved when all 6 residences have been visited.
Hello everybody, I'm Wong Ziyang, and I'll be talking about uniform cost search. UCS is an uninformed search algorithm, meaning it does not use heuristic information. Instead, UCS expands nodes according to their cumulative path cost from the starting point. In simple terms, the algorithm always chooses the partial route with the lowest total distance traveled so far before exploring other routes. In our implementation, the frontier stores possible routes, and before each expansion, the frontier is sorted by total cost so that the lowest cost route is expanded first. In the UCS process, the algorithm begins from Sunway University with a total cost of 0. It then repeatedly selects the route with the lowest cumulative cost from the frontier. When the algorithm moves to a new location, it updates the route path, adds the travel distance to the total cost, and marks the resident as visited if it has not been visited already. The process continues until all 6 residences are included in the visited list. In terms of evaluation, UCS is complete in this problem because it can find a solution if one exists, and it only terminates when the goal state is found or when the frontier becomes empty. UCS is also optimal because it expands routes in increasing order of cumulative costs. So the return route is guaranteed to be the lowest cost route when all travel costs are positive. However, UCS has high time and space complexity. In our implementation, it expanded a grand total of 114 nodes, which is considered high given that we only have 7 locations. It also stores many partial routes in the frontier and check states in the explored list. Therefore, UCS is only practical for this small-scale route planning problem because it successfully finds the optimal route for 24.15 kilometers. However, it may become less practical for larger real-world problems due to higher time and memory requirements.
A-star is an informed search algorithm that evaluates each node using Fn equals to Gn plus Hn, where the Gn is the actual distance traveled from the start and Hn is an estimate of the remaining distance needed to visit all unvisited residents. At each step, S-star expands the nodes with the lowest Fn value, prioritizing routes that are both efficiency so far and promising for the future. To guarantee an optimum solution, the heuristic must be admissible, meaning it never overestimates the true remaining cost. In this problem, the heuristic is calculated by summing the cheapest incoming age for each unvisited residence, ensuring it remains admissible. The result we get are Summer Universities to Nadayu, Sanyu, Emerin, Southling, Danao, and Needles, with a total of 24.15 kms in 25 nodes. The one key insight from our analysis, which is we get the same two locations visits through different paths using different f value. Initially, somewhere unique goes to Nadayus, then go to the Sanyus, give the f value of 17.85. But from somewhere unique go to Sanyu, then Nadayu gives a different value which equals to 18.95. The same distance travel, but the second pass loses the cheap Sanyus to Emerin edge, so the heuristics rise. A star correctly identifies the first part as more promising. In the result, A star is complete and optimum. 24.15 km is guaranteed. It expanded 25 node, far fewer than UCS at 114, and just slightly more than GBFS at 21. The strings are clear, it is accurate, efficiency, and scale better than UCS. While the weakness are heuristic dependency and memory. If the heuristic is poorly designed and overestimate, the optimality breaks. And since A star store all the generic state, memory grows with problem size, while it is still manageable here with 7 locations, but a concert at scale.
Next, I will explain greedy best first search. GBFS is an informed search algorithm, which means it uses extra information called heuristic to guide its decisions. The main idea is very simple. It always selects the locations that appear closest to the goal. In our case, this means choose the nearest and visit residential locations at each step. However, one important limitation is that GBFS only considers the heuristic value, which is Hn, and it's not the actual distance already traveled, which is Gn. Because of this, it can make fast decisions, but those decisions are not always optimal. In our road planning problems, we define the heuristic function as the distance from the current locations to the nearest unvisited locations. The process starts from somewhere university. From there, the algorithms evaluate all nearby locations and selects the closest one. For example, it first choose Nadayu 28 residents, then move to Sanyu resident, followed by Emerin, Southling, Danao Villa, and finally Nidox, by always selecting the nearest next locations. GBFS is able to construct a complete route efficiently. The final route generated has a total distance of 24.15 kilometers. In terms of performance, GPF is the fastest among the three algorithms. It expanded only 21 nodes and completed the search in a very short time. The main advantage of GPFF is that it is simple and efficient. However, its main weakness is that it cannot guarantee the shortest path because it does not consider the total travel cost. So, in conclusion, GBFS is a very useful when you need a fast solutions, but it might not always give a most optimal route compared to the algorithms like A star.
Hi, I'm Shang Hao. Let's move on to the comparison section. In this section, we compare the performance of the three search algorithms, namely UCS, A-star search, and really best first search, in solving the road planning problem. Firstly, uniform cost search UCS is an uninformed search algorithm that ensures both completeness and optimality. It always finds the shortest road, but it requires exploring a large number of nodes, resulting in higher time and space complexity. Secondly, A-star search is an informed search algorithm that combines the actual path cost with heuristic information. Similar to UCS, it ensures an optimal solution, but it expands fewer nodes and achieves better efficiency. Hence, it provides a good balance between solution quality and computational cost. Lastly, greedy best first search uses only heuristic information to select the next node. Therefore, it has the fastest execution time and requires less computational effort. However, it does not guarantee the optimal route, which means the total distance found may be longer than the optimal solution. Based on the experimental results, we observed differences in total distance, nodes expanded, and execution time among the three algorithms. Although GBFS is faster, it sacrifices optimality. UCS guarantees the shortest path but requires more computational resources. Among these three algorithms, A-star search provides the best trade-off between efficiency and optimality. In conclusion, A-star search is the most suitable algorithm for this route planning problem, as it is able to find the optimal route while reducing the search cost and improving overall performance.